Here we go with part 2 of section 5.4. These notes have to do with flux, magnetic fields, and currents. Here's our first example for this video. A coil with 25 turns of wire is wrapped around a hollow tube with an area of 1.8 meters squared. That's quite large. Each turn has the same area as the tube. A uniform magnetic field is applied at a right angle to the plane of the coil. If the field increases uniformly from 0 Tesla to 0.55 Tesla in 0.85 seconds, find the magnitude of the induced EMF in the coil. Okay, so the situation here, let's see if I can try to draw this. Here's the tube. Oops. Here's the end of the tube, rather. And then we're going to have a wire wrapped around the tube. And I'm not going to draw all of it, but it's going to be 25 turns. Now, when we have 25 turns with a cross-sectional area of 1.5, what did it say? Or 1.8 square meters, it's essentially like making a bigger area. It's going to induce more current. So I'm going to find that total area, 25 times 1.8, it's like having 45 square meters. Okay, then what's going to happen is we're going to have this bar magnet. I have so much fun drawing, I gotta remind myself that that's not what it's all about, but just draw this bar magnet a little bit. And it's gonna have a north pole and a south pole, and it's got a magnetic field associated with it. And the magnetic field around the magnet is going to be 0.55 Tesla. And what's going to happen is we're going to put this magnet into the coil, and when we put that magnet into the coil, it's going to induce a voltage in the coil. So we've got the total area computed here. We've got the B field, 0.55 Tesla. And the change in magnetic field is going to be the final value minus the initial value. We start with an initial magnetic field of 0, and then we put the magnet in and increase the magnetic field. So the change is going to be 0.55 Tesla. And the change in time, this happens over time. The change in time is 0.85 seconds. So the induced EMF, or the voltage induced, is equal to the opposite of the change in flux over the change in time. If I make a substitution here, this time what's changing is the magnetic field. So it's delta B times A times the cosine of the angle over delta T. Now in this case, the angle vector, remember, the angle vector is perpendicular to the area. I'm sorry, the area vector is perpendicular to the plane of the area. So the area vector is along that axis. So my angle is going to be 0 degrees. It's going to be parallel to my B field because the B field is like that. Now we're going to get different signs of EMF depending on whether we're putting the north end into the coil or taking it out of the coil. Draw this a little bit better. Okay, so but let's compute the amount of EMF first. So we're going to take negative delta B, which is 0.55, times the area, which was 45, times the cosine of 0, which is 1, over delta T, which is 0.85. So I get an EMF of, an induced EMF of 29.1 volts. Okay, now what we need to think about is what would the direction of that be? And I'm going to add a page to make some space for myself here. Okay, that turned out pretty good. I'm going to delete the parts of this that I don't need. I'm not going to worry about the numbers right now. Now we're going to talk about the direction. Okay. So let's think about this. Oh, let me fix this a little bit. Whoopsie. I don't want to take that with. Delete just a little more. Clean it up. Okay, sorry folks, almost there. All right, so here's the deal. When I take this magnet and I push it into the tube, what's going to happen is the magnetic field created by the current in this wire will oppose the motion. In other words, I'm going to have to do work to push this magnet into the tube. As I get closer and closer into the tube, it's going to take force for me to push this into the tube, which means the magnetic field created is going to be that this end is going to be, the right end is going to be the north end of the electromagnet, and this end is going to be the south end of the electromagnet. So while I am pushing the magnet into the tube, in order for that to be the north end of the electromagnet, what I'm going to do is I'm actually holding my pen in my hand and wrapping my fingers around and putting my thumb to the right, and that's telling me that the current then would be coming over the top like this. So that would be the direction of the current. Now, if I had the whole thing here, that's not 25 turns, but pretend it is for a second. I know that the positive terminal of the battery would be hooked up to that side of the coil to make the current go in that direction. And again, I'm going to draw a terrible picture here. What I'm doing with my right hand rule to determine this is I put a pencil or a pen in my hand. The pointy end is the north end of the electromagnet. I put my thumb in the direction of that, and then I wrap my fingers around it. And my fingers are coming over the top, and that's how I know that the current would be coming over the top. That would be the orientation of the current. What would happen then if I were to pull the magnet out. If I pull the magnet out, then the current's going to go in the opposite direction. All right, let's look at part B here. If the resistance in the coil is 2.5 ohms, find the magnitude of the induced current in the coil. Well, this is just an Ohm's law question. So we've got the 29.1 volts. We want the current, and the resistance is 2.5. So the current is 11.6 amps. All right. I think I've got one more example here. Here it is. A single circular loop with radius 22 centimeters is placed in a uniform external magnetic field with a strength of 0.5 Tesla so that the plane of the coil is perpendicular to the field. The coil is pulled steadily out of the field in 0.25 seconds. Find the average induced EMF during this interval. Okay, so I'm going to start by drawing a picture of this. Let's see, I'm going to draw my circular loop in the plane of the page. I'm going to have to decide something about how to do that. And let's see, that means that the magnetic field is either going to be going into the page or coming out of the page. I'll have it going into the page. And so again, the scenario is that this loop is in the magnetic field, and we're going to pull it out of the field. So by doing that, we are changing the effective magnetic field strength. So a couple things. Let's see. We've got the radius of the loop is 0.22 meters. So we can get the area of the loop is pi r squared, which is 3.14 times 0.22 squared. So that is 0.152 square meters. That's my initial area. And my final area is 0. My magnetic field strength is 0.50 Tesla. I guess I could think about it as changing the field strength or changing the area. I guess I'll think about it as changing the area. And I'm going to use the same formula as last time. EMF is equal to negative change in flux over change in time. Change in flux is, can't seem to make up my mind here, is opposite B times the change in the area times the cosine of 0 degrees over delta t. Again, remember that the area vector is perpendicular to the plane. Could be going into the page or out of the page. Let's see. Now I can plug in what I've got here. So this would be final minus initial. This would be 0.152 minus 0. And my time is 0.25. So when I solve that, I get negative 0.304 volts. Really what I want to concentrate on here is the amount and